So, welcome to this is lecture number 31 in our discussion of fluid mechanics. We have completed a couple of topics so far. We first derived the conservation equations for mass and momentum for a Newtonian fluid, and then we were looking at limiting cases. The first is the limit of low Reynolds number, where one can neglect inertial effects in comparison to viscous effects. In that case, we saw we could derive linearized equations for the pressure and the velocity field, and we looked at various ways of solving these equations. Then we switched over to the limit of high Reynolds number, and in the limit of high Reynolds number, of course, you neglect viscosity in comparison to inertia. We looked at a specific case. One is inviscid, viscosity is 0. The second is irrotational, that is, the vorticity is 0 everywhere within the flow. And in that case, we had derived the potential flow equations. Since the vorticity is 0, the velocity can be expressed as the gradient of a potential, and the pressure is given by a scalar equation, the Bernoulli equation, which relates the pressure to the kinetic energy per unit volume as well as the change in the potential with respect to time. And while discussing potential flows, we had noted that since we are neglecting the viscous terms, there is no momentum diffusion taking place, there is only momentum convection. A consequence of that is that we cannot satisfy tangential velocity boundary conditions at surfaces. Mathematically, the reason is because we are neglecting the highest derivatives. The original equation was a second order differential equation for the velocity vector u, and that had two boundary conditions at each surface, the no slip condition in the case of solid surfaces, that is, both the tangential and the normal components of the velocity are 0 at these surfaces. In the case of liquid gas, of course, there is a 0 shear stress condition and the normal stress balance condition. Since we neglected the viscous terms in the conservation equation, it was reduced to a first order equation, and for these potential flow solutions, we were able to satisfy only the normal velocity or the normal stress conditions at the surfaces. Mathematically, the reason was because we reduced the equation from a second order to a first order differential equation. Physically, the reason is that we neglected the diffusive transport of momentum. The flow along a surface, since there is a no penetration condition at the surface, the flow takes place tangential to the surface. Convective transport of momentum takes place only along the direction of flow. Therefore, convective momentum transport takes place only tangential to the surface. If you neglect momentum diffusion, there is no transport of momentum perpendicular to the surface. And this transfer of momentum perpendicular to the surface is necessary if you want to slow down the fluid at the surface. You have a free stream which is going at a finite velocity. If that velocity has to come down to 0 at the surface itself, there has to be the diffusive transport of momentum at the surface. Without that, you will not be able to satisfy the tangential velocity boundary conditions at the surface. So, the next topic is going to be boundary layer theory. In this case, we take into account the the diffusive transport of momentum perpendicular to the surface within a thin layer near the surface in the limit of high Reynolds number. So, that is going to be the next topic of our study, boundary layer theory. The simplest situation to consider is, of course, the flow over a flat plate. Let us say you have a plate of infinitesimal thickness in a fluid, and the fluid is moving with a constant velocity far from the plate. So, if I have a plate it has a certain length L. Okay, so this is a solid plate, it has a certain length L, and I have fluid incident on this plate far away. Okay. And of course, at the surface of the plate itself, you are satisfying the no slip boundary conditions at the plate surface itself. Okay. This is a symmetric configuration, so we can, without loss of generality, just analyze the flow above the plate. Okay. Two-dimensional system, I assume that the plate is of infinite extent in the direction perpendicular to the board. Okay. So, we use a two-dimensional coordinate system. Okay. The streamwise direction is x, the cross stream direction is y. Okay. And the free stream, the velocity, is coming in with a velocity capital U. Okay. That means that far from the plate, the velocity is equal to capital U. Okay. Since this is a two-dimensional system, I can use a two-dimensional equations to analyze this problem. Okay. So, first things first, what are the boundary conditions for this flow? Okay. You require that at the surface of the plate itself, both components of the velocity, streamwise and cross stream, have to come down to 0. Okay. The surface of the plate is at y is equal to 0 and for x greater than 0. For x less than 0, of course, in the coordinate system that I have used over here, there is no plate, so the velocity can have any value. But for x greater than 0, the velocity has to come back down to 0 at the surface of the plate. That is, both components of the velocity have to come to 0 at the surface of the plate. Okay. So, the boundary conditions are at y is equal to 0, okay, ux is equal to 0 and uy is equal to 0. Okay. Note that this holds only for x greater than 0. Because the plate is present only when x is greater than 0. If you go far from the plate in the y direction, you encounter the free stream. The fluid far from the plate has not really encountered the plate yet, okay, because it is at large distance away from the plate. The velocity should be just equal to the free stream velocity capital U. Okay. So, the second boundary conditions is that as y goes to infinity, ux is equal to just the free stream velocity u. Okay. As y goes to infinity, okay, ux is equal to just the free stream velocity u. Okay. The next boundary condition, these are in the y coordinate. We will see later that we need one condition in the x coordinate as well. Okay. That condition is that for x less than 0, note that we are assuming this is a high Reynolds number flow. Okay, this flow is a high Reynolds number flow. So, the fluid is being swept past this plate at high velocity. Fluid that is at x less than 0 has not encountered the plate as yet, because it is being swept past at high velocity. Fluid that is at x less than 0 has not encountered the plate yet. Okay. Therefore, you would require that the fluid has to have just the free stream velocity for x less than 0. Okay. ux is equal to just capital U for all y. Okay. So, that is the third boundary condition for x less than or equal to 0. ux is equal to capital U for all y. The fluid that is upstream of the plate can encounter the plate only due to momentum diffusion in that direction. Okay. The point to note is that the fluid upstream of the plate, if the convective effect is going to only convective transport is going to only affect positions that are downstream of the location, okay, not positions that are upstream, because convection takes place in the direction of the fluid flow. Therefore, locations upstream of the plate can sense or can be affected by the plate only if there is momentum diffusion in that direction. We will see a little later that momentum diffusion in the streamwise direction is small compared to the cross stream direction, and we can neglect it. In that case, the fluid upstream of the plate has not yet encountered the plate because there is no diffusion of momentum in that direction. And that is the reason for this boundary condition. We will see a little later how this fits in naturally into the framework that we will develop. So, now that we have the configuration and the boundary conditions, let us go on to the equations themselves. Okay. So, the equations in the x and y directions. Okay. We can first write down the equations in the vector notation. Okay. Partial ui by partial xi is equal to 0 and rho this is a steady state configuration, therefore, I will neglect the time derivative of the velocity field, since I am not looking at variations of the velocity with respect to time. Okay. So, I will just take the convective term alone. So, these are the vector equations, and one can write it down in terms of the components, because this is only a two dimensional system. Okay. So, if I write down in terms of the components of the equations, I will get rho into ux partial ux by partial x that was the x momentum conservation equation, and I have a similar y momentum conservation equation, which is rho into yes, that is the y momentum conservation equation. Note that to get these equations, if you start off with this equation, okay, I is the free index, it represents the vector direction. Okay. So, in order to get the x momentum conservation equation, you would set I is equal to x in this indicial in this equation written in indicial notation. J is repeated, it is summed over. So, it sum over j is equal to x and j is equal to y for a particular value of I. I is x for the x momentum equation and I is y for the y momentum equation. You sum over the values of j is equal to x and y. Okay. So, we can do the usual scaling in this case. Okay. The natural scale for x has to be the plate length L. Note that there is no other length scale in the problem. The plate is an infinitesimal thickness, it has a length L. So, I would naturally scale the length by the plate length L. Okay. Similarly, for y, because there is no other length scale in the problem. Okay. And if you are scaling the length, the distances by L, you would naturally scale velocities by the free stream velocity capital U. Okay. So, you define ux star is equal to ux by u and uy star is equal to uy by u. Okay. Put that into the equation. Okay. You put it into the equation, and I will not go into the details, it is quite easy to obtain. Okay. What you will get is rho u square by L into ux partial ux by partial x Okay. So, that is what you get for the x equation, and similarly for the y equation you will get So, that is what you get for the x and the y equations. There should be a rho u square by L here. Okay. Since I am considering the limit of high Reynolds number, I scale it by the inertial scales, in which case my scaled pressure P star will be equal to P by rho u square. Okay. My scaled pressure P star will be equal to P by rho u square. Okay. And once you have done that, you can divide throughout by this prefactor here. Okay. Divide throughout by this prefactor here, rho u square by L, okay, on both sides of the equation. Okay. When expressed in terms of P star, okay, this length scale will disappear. Okay. And when I divide throughout by rho u square by L, this just becomes equal to inverse of Reynolds number. Okay. Okay. Where the Reynolds number is defined as rho u L by mu, which is also equivalent to u L by nu. This is the Reynolds number based upon the free stream velocity and the length of the plate. Okay. And if we consider the limit of high Reynolds number, then of course these two terms go away. Okay. If we consider the limit of high Reynolds number, we no longer have the diffusion terms, the viscous terms. Okay. And therefore, my equation just reduces to a first order equation of the form is equal to minus partial P by partial x I star. This reduces to a first order differential equation. In this particular case, for the flow around a flat plate, the pressure gradient turns out to be equal to 0. Okay, the pressure gradient turns out to be equal to 0, because far away the equations are inviscid and I just have a constant pressure everywhere. So, since the pressure gradient turns out to be equal to 0, I just find that u dot grad u is equal to 0. Okay. If you recall, when we did mass and energy conservation, we had a similar expression of the form u dot grad c is equal to 0, okay, in the case of high Peckley number flows which are convection dominated. The equivalent in this case, in the absence of a pressure gradient, is just u dot grad u is equal to 0. I told you that when u dot grad c is equal to 0 implies that the concentration does not vary along streamlines. Okay. Similarly, in this case, u dot grad u is equal to 0. The velocity does not vary along streamlines, the velocity is a constant along streamlines. And what that implies is that the velocity along any streamline is just independent of the streamline along which as you go down the streamline, the velocity is independent of the streamline. Okay. With that, there is no way to satisfy the 0 velocity boundary condition at the surface itself. Okay. That is because, as I said, I have neglected momentum diffusion. Okay. And when I neglect momentum diffusion, there is no mechanism for the velocity of the fluid to be influenced by the surface itself. There is no way for the surface to exert a tangential stress on the fluid. Okay. But of course, in a real system, the velocity does have to come to 0 at the surface. In a real flow, the velocity does have to come to 0 at the surface. Okay. And the reason it comes to 0 is the following. Okay. If you recall, in this equation, I have neglected these terms. Okay. I have neglected these momentum diffusion terms. That is because the Reynolds number is large and therefore Re inverse is small. Okay. Re was calculated assuming that the relevant length scale is the length of the plate itself. Okay. The Reynolds number was calculated assuming that the relevant length scale is the length of the plate itself. Okay. That means that the relevant gradient goes as the mean velocity, the free stream velocity divided by L. Okay. So, what I have assumed is that the length scale, okay, okay, xi goes as L, which implies that partial by partial xi goes as 1 over L. Okay. That is, gradients will scale as the quantity divided by L. that is the variation in that quantity takes place over a distance comparable to the length of the plate L, because that is the only length scale in the system. Okay. On that basis, we find that the diffusion terms are Re inverse smaller than the convection terms. Okay. However, that does not satisfy the boundary conditions. The velocity has to come to 0. Okay. What is the answer to this paradox? Okay. The answer is that if the velocity variation takes place over a length which is smaller than L, if the velocity variation takes place over a length scale which is much smaller than L, then the gradients are much larger than 1 over L. Okay. If the variation velocity, for example, in this particular case we are interested in diffusion perpendicular to the flow. Okay. So, if the length scale for the y direction is some length delta which is smaller than L, it will imply that partial by partial y goes as 1 over delta, okay, which is much larger than 1 over L. And I have second derivatives on the right hand side with respect to the y coordinate. Okay. So, I could have a situation where delta is becoming much smaller than L. Okay. So, that 1 over delta square is much larger than 1 over L square. Okay. So, I have a second derivative here on this term. Okay. I have a second derivative here on this term that multiplies this Re inverse. Reynolds number is large. So, Re inverse is small. Okay. That was based upon the length of the plate. On the velocity, I have a second derivative. If the length scale for that is small, if it goes as delta, the second derivative goes as 1 over delta square. And I could have a situation where the product of these two, 1 over delta square is a large number, Re inverse is a small number. I could have a situation where the product of these two is of the same magnitude as all of the other terms in the momentum conservation equation. In particular, the product of these two is of the same magnitude as the convective terms. If that happens, I have a balance between convection and diffusion, and then I can satisfy the boundary conditions. Okay. This balance has to hold in the limit as Re goes to infinity. Okay. As I make Re larger and larger, okay, the Reynolds number based upon the plate length becomes larger and larger, the length scale delta becomes smaller and smaller in such a way that this second derivative times Re inverse is always of the same magnitude. It does not go to infinity, it does not go to 0. In the limit as Re goes to infinity, this remains finite, okay, and it always balances the inertial terms. That is the only way you will be able to get a situation where you can satisfy the boundary conditions in the for the tangential velocity. So, what do we do now? We rescale our equations, postulate that the length scale perpendicular to the surface of the plate is some small length delta. Okay. I require that because ultimately, unless the diffusion term balances the convection term, there is no way to satisfy the boundary conditions. I postulate that it is a length delta, and I will get what is the length scale delta from the condition that in the limit as Re goes to infinity, this term remains finite, okay, and of the same magnitude as the inertial terms. Okay. So, that is the condition that I will use. So, let us do that rescaling. Okay. So, basically I have a plate of total length L. Okay. I assume that there is some small length delta here which is much smaller than L. Okay. This is the x and this is the y direction, okay, and they have a free stream fluid coming in. So, I have the small length delta. The length scale in the streamwise direction is still L, because that is the length scale over which the flow varies in the streamwise direction, okay, because the plate length is L. That sets the length scale for the variation in the streamwise direction. Okay. So, I define x star is equal to x by L. That is the length in the streamwise direction, and the scaled y velocity is y by delta. I do not yet know what delta is. I will choose it from the requirement that the diffusion or the viscous and the inertial terms continue to be of the same magnitude in the limit as Re goes to 0. In other words, as Re becomes larger and larger, delta has to become smaller and smaller in such a way that the second derivative of the velocity times Re inverse remains of the same magnitude. The length scale, the scale for the velocity is equal to ux by u, because far away from the plate the velocity is capital U, at the surface it has to come down to 0, therefore, it has to vary between 0 and capital U. So, u is the free stream velocity. What about the velocity perpendicular to the plate in the cross stream direction? The scaling, obviously the velocity perpendicular you would expect it to be 0 far away from the plate, okay, because far away from the plate you just have a unidirectional flow with a constant velocity capital U. Okay. You would expect it to be small far away from the plate. What about the velocity u at the surface of the plate itself? The velocity scale for that is not capital U. Okay. One has to be careful when evaluating this velocity scale. The way you get it is by going to the mass conservation equation and scaling all terms in the mass conservation equation. So, the mass conservation equation is del dot u is equal to 0, which implies that partial ux by partial x plus is equal to 0. I expressed each of these in terms of the scaled variables. Okay. So, ux is equal to capital U times ux star and x is equal to capital L times x star. Okay. So, I will get u by L partial ux star by partial x star plus I do not yet have a scaling for uy yet, okay, but I will scale delta and then from that determine what is the scaling for ui. Okay. So, this becomes 1 by delta partial uy by partial y star is equal to 0. Divide throughout by the prefactor of the first term, okay, that is the simplest thing you can do, okay, and you will get partial ux by partial x plus L by delta u partial uy this is equal to 0. Now, all terms in the equation here are dimensionless except the uy term. Okay. So, it is natural to define a scaled variable uy as uy star is equal to uy by u delta by L. Okay. And with that the mass conservation equation just becomes partial ux by partial x plus partial uy is equal to 0. Okay. Note the velocity scale for uy. Okay. The velocity scale for uy is u delta by L. Okay. The velocity scale for uy is u delta by L. We postulated that delta was small compared to L. Therefore, the velocity in the y direction is small compared to the velocity in the x direction. Okay. This is a natural consequence of the mass conservation equation, because the mass conservation equation is telling you that the scale for ux by the scale for x has to be the same as the scale for uy divided by the scale for y. Okay. So, this is a natural consequence of the mass conservation condition. So, there is a scaled mass conservation equation which has given us a scaling for the velocity uy. Okay. So, next let us go to the momentum conservation equation. So, the momentum conservation equation in the x direction. Okay. First, we will take the x momentum conservation equation, because it is the x velocity that we were having difficulty with the boundary condition. We had required that the x velocity has to come to 0 at the plate, that is the tangential velocity has to come to 0 at the plate. The potential flow equations were not giving us that, because we could not satisfy the tangential velocity boundary conditions. Therefore, we first analyzed the x momentum equation, because somehow we have to get the diffusion or the viscous and the inertial terms to be comparable in order to be able to satisfy this boundary condition for the x velocity. Okay. and now we express each term in this equation in terms of the scaled variables. Okay. So, the first term, it has 2 u x. Okay. U x is equal to capital U times u x star. So, I have u square, and x is x star times L. So, I will get u square by L, u x star partial u x. Okay. The second term u y, u delta by L, okay, times u x, which is u divided by delta. Okay. So, I will get u delta by L into partial u x by partial y will be u by delta. Okay. The pressure, okay, we have not scaled the pressure yet. The pressure scaling will come out of the requirement of scaling all the other terms in the equations. So, we will just leave the pressure for the moment. This is equal to minus 1 over L partial P by partial x star, okay, plus, okay, the viscosity into the scaling for u is u x is capital U, the scaling for x square is L square partial square u x by partial x square plus u by the scaling for y is now delta square. Okay. The scaling for y is delta, therefore, partial square u x by partial y square will be u by delta square partial square u x star by partial y star square. Okay. You can see that the first term in the equation, the convective term, it has a common factor rho u square by L. Okay. It has a common factor rho u square by L. Okay. So, let us take that out. Okay. I have rho u square by L into partial u x by partial x. Okay. It's equal to minus 1 over L partial P by partial x. In this second term, in the viscous term, I have 2 terms. Okay. That is the streamwise second derivative of the velocity and the cross stream second spatial derivative of the velocity. You can easily see that the cross stream second derivative is much larger than the streamwise, because the cross stream derivative goes as u by delta square, the streamwise goes as u by L square, and we have postulated that delta is much smaller than L. Therefore, 1 by delta square is much larger than 1 over L square. So, I will take that 1 over delta square as the common factor out. Okay. So, this becomes mu u by delta square into partial square u x by partial y square, okay, plus a second term which goes as delta square by L square partial square u x by partial x square. Okay. You can see that this term here, this term here multiplied by u by delta square here gives me back u by L square, which is the prefactor of partial square u x by partial x square. Okay. So, I have just taken one common factor out. I have taken the largest factor as the one in front, because I would expect the largest term to be one that balances the inertial terms. Okay. So, I divide throughout by rho u square by L. Okay. You divide throughout by rho u square by L, and once you do that, that gives you a scaling for the pressure. Okay. Because when I divide throughout by rho u square by L, the prefactor of the pressure gradient is just 1 over rho u square. Okay. So, I define P star is equal to P by rho u square, and my equation becomes u x partial u x by partial x is equal to minus partial P by partial x plus mu L by rho u delta square, okay, divided throughout by rho u square by L, and the prefactor of the viscous term becomes mu L by rho u delta square. Okay. Okay. So, this illustrates what I had tried to explain a little earlier, that in this particular case, since the length scale in the streamwise direction is large compared to the length scale in the cross stream direction, the diffusion term in the streamwise direction, second derivative with respect to the streamwise coordinate, is much smaller than the diffusion term in the cross stream direction. Okay. So, therefore, I can neglect streamwise diffusion in comparison to cross stream diffusion, because the smaller thickness and the larger gradient is in the cross stream direction. Okay. So, I neglect this, okay. And obviously, there is going to be a balance between diffusion and or between viscosity and inertia, or between convection and diffusion in the limit as R e goes to infinity, only if this term continues to remain of order 1 in the limit as R e goes to infinity. Okay. So, I require that the boundary layer thickness delta should be such that this term continues to be finite. It does not go to 0, does not go to infinity. It goes as R e to the 0th power. Okay. It is independent of Reynolds number in the limit of R e going to infinity. So, as the Reynolds number goes to infinity, this term has to be independent of the Reynolds number. Okay. So, I require that rho u delta square by mu L is equal to some finite number. Okay. I will call it as order 1. It goes neither as R e to a positive power nor as R e to a negative power. If it goes as R e to a negative power, it will go to 0, and then my viscous term will become small compared to the inertial term. If it goes as R e to a positive power, it will go to infinity, and I still do not have a balance, because there is nothing to balance the viscous term here. Okay. I can rewrite this as rho u L by mu into delta by L the whole square is equal to some number. Okay. Let us is equal to some constant. Okay. It is a number that remains finite as R e goes to infinity. That means that this rho u L by mu is the Reynolds number itself. Okay. Rho u L by mu is the Reynolds number itself. Okay. That means that delta by L the whole square has to be equal to C times R e power minus half. I am sorry. Okay. That is, delta by L has to decrease to 0 as the Reynolds number to the minus half power in the limit as R e goes to infinity. Only then will the viscous term continue to be of the same magnitude as the inertial term, even in the limit as R e goes to infinity. Let us look at this a little bit. Okay. So, what this is saying is that I have a boundary layer thickness. The thickness becomes smaller and smaller, proportional to R e power minus half in the limit as R e goes to infinity, in such a way that the balance between the inertial and the viscous term continues to balance out, even as the Reynolds number becomes larger and larger. This delta itself is just a length scale that I had used for scaling my equations. Okay. Delta, of course, you require that it has to remain a constant, okay, in the limit as R e goes, I am sorry, it has to go as constant times R e power minus half in the limit as R e goes to infinity. However, that constant is just a length scale, so it can be set to any value, okay, without loss of generality. This constant can be set to any value. Okay. The equations written in terms of the scaled variables will change with a change in the value of the constant. However, the equations written in terms of unscaled variables will not change, because that delta is only a length scale I am using to non-dimensionalize the coordinate. Okay. So, without loss of generality, you can just set this constant as 1, okay, and write delta by L is equal to R e power minus half, okay, because any value of the constant will change the solution expressed in terms of the scaled variable, because I am using this delta to scale the variables. However, it will not change the solution in terms of the unscaled variable, because ultimately when I convert back to the unscaled variable, I will end up with the same solution once again, because the equation itself has only one solution. So, this has given us the dependence of delta on Re in such a way that the viscous and inertial terms continue to balance each other even in the limit as Re goes to infinity. So, this was for the x momentum conservation equation. Next, we go on to the y momentum conservation equation. The y momentum conservation equation is ux partial uy times rho is equal to minus partial p by partial y plus mu and once again we express this in terms of the scaled variables. Ux star is equal to ux by u, uy star is equal to uy by u delta by L, x star is equal to x by L, y star is equal to y by delta is equal to p by rho. So, I express my equations in terms of this. Okay. So, first term rho, ux has a factor of u, uy has a factor of u delta by L, and there is a 1 over L derivative with respect to x. Okay. The second term is second order in uy, it contains uy times uy. So, you will get u delta by L the whole square into there is the derivative with respect to y. So, this is equal becomes 1 over delta. Okay. Pressure scaling is rho u square, y is delta. So, this becomes minus rho u square by delta plus there is the viscous term uy is u delta by L into 1 by L square partial square uy star As you can see, for the convective term, the total prefactor is u square delta by L square. Okay, after you multiply all the terms there, you get a common factor of u square delta by L square. Okay, so, you get rho u square delta by L square plus the viscous term. Okay, so, let me just write that down here. Once again, the largest viscous term is the derivative in the cross stream direction, because 1 over delta square is much larger than 1 over L square. Okay. Therefore, I will take that out as a common prefactor, because I have to take the largest term out as a common prefactor. Okay. That is the momentum conservation equation in the y direction. As usual, I can neglect streamwise diffusion with respect to cross stream diffusion, because the length scale in the cross stream direction is much smaller. You can see that here as well. The cross stream, the streamwise diffusion term contains a factor of delta by L the whole square. That can be neglected with respect to the cross stream diffusion term. Okay, so I can always neglect the streamwise diffusion with respect to the cross stream diffusion. Okay. And I divide throughout by the largest term in this equation. Which is the largest term in this equation? Okay. No, it is not the convective term. You can see the convective term goes as rho u square delta by L square. The pressure gradient goes as rho u square by delta. Okay. Pressure gradient contains 1 over delta, whereas the convective term contains delta by L, rho u square by L times delta by L. So, the largest term is actually this one. It contains a delta in the denominator, and delta is a small number compared to L. Okay. So, I divide throughout by the prefactor of this term to get a dimensionless equation. Okay. If I divide throughout by the prefactor, what I will get is on the left side, I will get delta square by L square into u x and for the second term what I will get is this term here contains mu u by L delta. Okay. It contains mu u by L delta. Okay. If I divide by rho u square by delta, you can easily verify that the resulting prefactor that you get will be mu by rho u L. Partial y square. Okay. You can see that this term contains a prefactor delta by L the whole square. Okay. Delta by L goes as r e power minus 1. So, in the limit as r e goes to infinity, delta by L the whole square goes as r e power minus 1, which goes to 0. Okay. This inertial term, this viscous term here contains a prefactor of 1 over Reynolds number. Reynolds number based upon the plate length L is also small, and therefore, this is also small. Okay. What ultimately the equation for the cross stream momentum reduces to is that the pressure gradient in the cross stream direction is equal to 0. Okay. The cross stream diffusion equation basically reduces to partial P by partial y is equal to 0. Okay. So, this gives me the simplified momentum equations in the x and y direction. In the y direction, the equation tells me that partial P by partial y is just equal to 0, and I have a momentum conservation equation in the x direction. Okay. I derive these equations by scaling, and I obtain reduced scaled equations. Okay. However, if these are the dominant terms in the scaled equations, they will also be the dominant terms in the original unscaled equations, because I get the scaled equations by dividing all terms by some factor. All terms in the equation are divided by the same factor. Therefore, if the scaled equations contain these as the dominant terms, then the unscaled equations will also contain these as the dominant terms. So, these are the boundary layer equations for the flow past any surface. Okay. In this particular case, we are considering just a flat plate, but for the flow past any surface, these are the boundary layer equations. Okay. These are the boundary layer equations for the boundary layer very close to solid surfaces. when the boundary layer thickness is restricted to a very small distance in the limit of high Reynolds number. Okay. So, these are the boundary layer equations. And these equations contain this additional viscous term here. Okay. Contains only the cross stream diffusion, because that is what is required to reduce the tangential velocity to 0 at the surface in the streamwise momentum equation. The cross stream velocity condition was already satisfied by the potential flow, the normal velocity condition. What we need to do is to satisfy the streamwise velocity condition. That is taken care of by adding this additional term. And a common feature of all boundary layer equations is that this pressure gradient in the cross stream direction is always equal to 0. Reason is because if you have to generate a pressure gradient in that direction, there has to be some flow in that direction. Okay. The velocity in the y direction in all of these boundary layer problems is always very small compared to the velocity in the x direction. Therefore, there is nothing to balance the pressure gradient in the cross stream direction, and in the leading approximation you always find that the pressure gradient in the cross stream direction is always equal to 0. The terms neglected here are Re inverse smaller than the term that is retained. Okay, so the terms that are neglected in this equation are Re inverse smaller than the term that is retained. Okay. Now, if we were to solve a boundary layer equation, we require that in the limit as y goes to infinity, the solution for the equation naturally goes over to the solution for the outer flow, the outer potential flow. Okay. So, in our flat plate case, for example, okay, we have a flat surface over here with two coordinates, x in the streamwise, y in the cross stream direction, and I have some kind of a boundary layer close to the surface where viscous effects are important. Viscous effects are comparable to inertial effects. Okay. The outer potential flow was specified with no viscosity in it. Okay. The outer potential flow was specified with no viscosity in it. Okay. So, if I consider the outer potential flow without incorporating the boundary layer momentum diffusion as some velocity u of x, okay, in this particular case it was a constant velocity. In the specific case that we were solving, we required that the velocity u was the same everywhere. Okay. Far away from the surface, but as we will see, there are other cases where there may be either acceleration or deceleration of the free stream flow far away from the surface, okay, in the x direction. Okay. So, for the outer flow you require that the flow has to satisfy the equation. Okay. Okay. For the outer flow there will be a smooth transition from the boundary layer flow to the outer flow if the outer flow, when viscosity is neglected, also satisfies the same equation. Okay. So, for the outer flow itself I require that capital U, okay, partial u by partial x, okay, this is the free stream velocity along the flow direction, okay, plus the cross stream velocity is equal to minus partial p by partial x. Okay. However, when I go far from the surface, the velocity u y goes to 0. Okay. The velocity u y is identically equal to 0 far from the surface, and therefore, this is equal to 0 for the outer flow. Let me call it as an inviscid flow. Okay. So, minus partial p by partial x is equal to u times partial u by partial x, where capital U is the outer potential flow. Okay. However, we know that partial p by partial y is equal to 0. At a given location x, the pressure itself does not depend upon y, okay. Regardless of what the distance from the surface is, the pressure is invariant in that direction. So, for a given x, the pressure is independent of y. In the limit as y goes to infinity, the pressure is given by this. Okay. The pressure is independent of y, that means that at any y, the pressure is given by this, okay, because I have the condition that the pressure is independent of y. In the limit as y goes to infinity, the pressure is given by u times partial u by partial x. That means that the pressure has to be given by u times partial u by partial x at any value of y. Okay. So, therefore, I can substitute this for the pressure gradient at any value of y, because I know that the pressure is independent of y. And my equation becomes u x partial u x by partial x plus u y is equal to u should have a row here. Plus mu partial square u x by. So, those are the boundary layer equations expressed in terms of the free stream velocity far from the surface. Far means that the distance from the surface is large compared to delta, because it is only over a distance comparable to delta that the momentum diffusion is comparable to the convective terms. When the distance from the surface becomes large compared to delta, momentum diffusion becomes small compared to convection. Okay. For our particular case of a flat plate, this is equal to 0, because capital U is just a constant. It is a free stream with a constant velocity far away. Therefore, capital U is just a constant. Therefore, this term is equal to 0. So, in the next lecture, we will solve this equation. There is one more little bit of information that we need before we solve this equation, and that is that the velocity at a given location x does not depend upon the total length L, but on the distance x itself, because the total length is downstream of the plate. We will use that in the next lecture in order to get a similarity solution for this flow past a flat plate. As you can see, the logic that we have used here is very similar to the logic that we had used previously in boundary layer theories for heat and mass transfer. It might be useful to go back and look at those calculations to see how we derive the scalings in those cases. The scalings in this case is also very similar. So, kindly go and have a look at that once again, and we will continue to get to proceed to get a similarity solution similar to what was done in heat and mass transfer in the next lecture. We will see you then.